So in this video we're going to look at the terms relative atomic mass and relative molecular mass and the sort of calculations that we might do with those. So the first one we're going to look at is relative atomic mass. So our relative atomic mass, our AR, is the weighted average mass of all the isotopes relative to 1/12 the mass of one atom of carbon-12. So what do we mean by the weighted average mass of all isotopes? If we consider a sample of chlorine atoms, for example, then what we find is there are two naturally occurring isotopes of chlorine, one that weighs 35 and one that weighs 37, but their average is not 36 because they are not in equal abundance. So we have to weight this average to do with the number that there are. So I've drawn a little diagram showing you the relative amounts, and you could count up how many of each there are. So we've got 5 in this sample atoms of chlorine 37, and we have 15 atoms of chlorine 35. So it's not true to say that if I took the average mass of this box it would weigh 36, because there's more things in it that weigh 35 than there are that weigh 37. So if we were to work out the total mass of the things that weigh 37, then we could multiply 37 by 5. If you type that on your calculator, you should get 185. And if we want to do the same for the ones that weigh 35, we should get 525. So in total, the sample actually weighs 710, and that is spread out over a total of 20 particles. So if we were to divide that number by the 20 atoms in my sample, then we'd find that the average mass is not actually 36 but 35.5, and that is what we mean by the weighted average. We're weighting it to take account of the numbers of each type of atom. So when we calculate this weighted mass, what we will find is the number in the periodic table. It's that number to one decimal place that's shown at the top. 24.3 is a weighted average. Because there are actually 3 isotopes of magnesium, and if we have a look at their percentages, we can understand why it's 24.3. So the 3 isotopes are magnesium 24, magnesium 25 and magnesium 26. Those 3 isotopes all have 12 protons but differing number of neutrons. If we then take into account that in a sample of 100 magnesiums, 79 of them will weigh 24, 10 of them will weigh 25 and 11 will weigh 26, we can get that weighted average as 24.3. So how do we do that? What is the calculation that we've just been looking at? And it goes like this. We're going to use the sum of, so that means add up, that little sigma, the sum of the mass times the abundant for each isotope. So in a minute we could have a look at doing that for our magnesiums above, divided by the total abundance. Now, if your abundances are given as percentages, that bottom number will be 100. But if, like my example of the chlorine, they don't add up to 100, we will divide by the total number that we had. So before we have a look at this example, why don't we try it with the magnesium? So these are our numbers. So if we've got 79%, or in every 100 that means 79 of them weigh 24, we could times the mass by the abundance, and then we're going to add that to the fact that 25, the mass times the abundance, there's 10 in every 100 weigh 25, and then we could add that to the mass times the abundance of the last one, and we're going to share that out between the entire sample. And in this case we've done percentages, so we've done it as out of 100, and this is going to give us our AR. So type that on your calculator and see what you get. So I got 24.32. The number in the periodic table is given to one decimal place, so we can see why that is 24.3 to 1 decimal place. So what I want you to do is have a go at the example in your pack. We've got copper, we've got 2 isotopes, find the relative atomic mass and give your answer to 3 significant figures. So if you've done that correctly, you should have got 63.6. So we're going to move on to look at relative molecular mass. So our relative molecular mass, or MR, is the mass of a molecule relative to 1/12 the mass of an atom of carbon-12. And this is found much more simply than finding the relative atomic mass, because we've got the relative atomic masses in the periodic table. We're just going to add up the relative atomic masses of the elements in the molecule, and we're going to take account of any numbers. So we're going to use our periodic table, and if you go to the periodic table and find the relative atomic mass of nitrogen, you'll see that it's 14.0. We've got 1 nitrogen in our molecule. There are then 3 hydrogens, and the relative atomic mass of hydrogen is 1.0. So we add up a 14 and 3 ones, and we get 17.0. See if you can do the next one yourself. So there you go, there were 2 carbons at 12, 4 hydrogens at 1.0, and 2 oxygens at 16. We add all that up, we should have got 60.0. Now, to be precise at A-level, what we need to consider is that actually, you'll remember from our introduction pack, only the covalent things are classed as molecules. So if something's ionic, we shouldn't really say relative molecular mass, and so we have a slightly different term, relative formula mass. It is still the mass of one formula unit, so one set of the chemicals, and so as far as you're concerned, for adding it up, it makes no difference. It's just a technicality that not everything's a molecule, so you shouldn't say relative molecular mass for everything, but you're going to add it up in exactly the same way. Have a go, see if you can add up these 2. So the first one, we've got 2 sodiums, 1 carbon and 3 oxygens, that comes to 106. Just watch out in the second one. There is 1 magnesium, but there's 2 nitrogens because there's 2 of this whole bracket, and there's 6 oxygens because 3 lots twice is 6, and so we're getting 148.3. So in this little section we've learned how to calculate the relative atomic mass using the weighted average, and how to add up relative atomic masses to calculate the relative molecular mass.